So first thing is assignments that are coming up. So we are starting chapter 5. If you haven't already done the prepare to learn and the vocabulary for chapter 5, make sure that you get that done because that was due last night. Um, and then active, which is going over calorimetry, which we're starting today, it will be due next Tuesday. You're going to be doing those calculations in lab next week. So I want you to make sure that you're looking at it before lab. So if you have Tuesday lab, try and get it done by Monday night so that, or at least look at it by Monday night so you know what you're doing in lab. Okay, so that's kind of those things. Don't forget there will be a quiz next week. So stoichiometry of gases, molarity, or not molarity, molar weight and density of gases, and then the calorimetry that we're looking at here. I have handed out to you a paper on the extra credit things that I've been putting in the folders over there. So the set that you will have due next, I won't collect it after the next test because I'll have ones that will be content that I'm not sure if it's going to make it onto the next test. So I'll just collect it the day of your final exam. That will be when that will be due. And the first one is, well, first of all, I haven't been really enforcing this stuff at the top, and I'm going to be more picky on that now because I've had so many like loose things coming in that it's like I have in 3 different places the same person stuff and they're not attached and things fall apart. So it either needs to be in a folder with your name on everything or attached to a notebook. So they're designed to fit in something this size. I have a few extras if you want to take one, or you can use a spiral notebook. Don't put it on loose leaf paper because then things get separated again. So if you're going to do that, it needs to go in a folder. But that's how I want it to come to me. Okay, so the first one on here has some bullet points underneath it, and that's this one. It's in the orange folder over there. And the first thing you'll do is just fold this in so that you're be looking at it this way, and that way the directions about where things are will make sense. There is a website for PhET. PhET has all kinds of simulations for different physics and chemistry and different kinds of things. So you can kind of see what would happen without being in lab. And so when you open this up, the middle area is where you will do those things. And so you'll follow the directions. There's 4 different tabs, and one of them says ideal, like ideal gases. One says energy, and you'll just follow those directions. Fill in the middle part first and then do the outside parts. If you start with where the arrows are, the questions won't make a lot of sense because you haven't collected the data yet. So that's why I suggest you kind of fold it in first so you have a sense of how this is going to work. And then ideally you would cut in between these so you could lift each flap at a time. This then will fit nicely into a notebook like this. The second one that I have is in the yellow folder over there. And so it's 2 pages. So the back page is what gets attached to the notebook. And you're going to write in your definitions and things. And then you're going to make it kind of a lift the flap kind of thing. So the top page has all the things you cut out and put on top of it. So you can say, oh, what are the units of heat? And lift it up. And then on the inside, it'll have the units of heat. One weird thing about this is that this middle area has a back to it. So if I open this up, you'll see on here, there's a back. So this is designed so the words face you when you attach it. So when you attach it, make the picture side down. And then when you open it, you'll see both what's on this and this for that. So this one's a little bit more involved, 2 points. This one's a lot more involved, up to 5 points. But remember, the extra credit isn't for the cutting and taping. The extra credit is for the chemistry part of it. So just cutting it out isn't going to get you anywhere. I want you to be thinking about how to put these things together. I would recommend that if you're going to do this one, sometime next week or maybe over this weekend, start working on it because it's going to be most helpful to you while we're learning this content. If you wait until the final exam, it might be a nice little review, but you're going to have so many other things on your mind, it's going to be less helpful then. So questions about those? All right. Now we are going to be jumping into chapter 5. I don't have your quiz grades recorded, so hopefully I will get those done this afternoon and I will get those quizzes back to you on Monday. So I think I now have everyone has taken the quiz. So there's that. Yes.
Do you think you'll have the numbers like over the weekend? Like you'll have.
My hope is tonight. My daughter is coming into town, and so new people in the house may make me forget what I'm doing. So hopefully before I leave work today, it will be in the computer. If not, I apologize, but that is my goal. Okay, so let me share this. Okay, so we are starting on chapter 5, which is all about thermochemistry, or the chemistry of heat, or sometimes we call it thermodynamics, which is changes in heat. So we need to talk about energy. We're most interested in heat energy in the chemistry, and I'll explain why in a minute. And that's why we're dealing with thermal. All right, so section 1 is just kind of giving us some vocabulary, some terminology, that kind of thing. And then section 2 is going to get into how we use it in calculations. All right, so what is energy? When I say I have no energy, I mean, I can't do anything. If I have lots of energy, I can run around and do a lot of stuff. So energy is associated with doing stuff. And in scientific terms, that would be work. So energy is the ability to do work. In scientific terms, work is moving a mass, something that has weight to it, in opposition to a force. Okay, so you probably remember from some science class that once we get an object moving, it tends to keep on moving. So just because it's moving doesn't mean that we're doing any work. We have to be doing it against some force that's resisting. And that might be friction, or it might be gravity. So if you stand up, the mass of your body is the mass, and the distance that you're moving your body is the distance, and the force is the gravity at work. So it's not all about work, it's also the capacity to supply heat. So I might have energy in the sense that my body is warm and I can supply heat to, my cat. If I cuddle with my cat, or my kid, if they're cold, I can supply heat to them. And so that also is having energy. We use a couple of different units. Joules is the SI, kind of the official units. And that means that it is based on about 5 different fundamental units. So it's based on kilograms, meters, and seconds. We can go back to those. And then somewhere it used to be there was an object that weighed 1 kilogram, and everybody would, compare to that particular object in order to determine how much a kilogram was. They've changed it, and I can't remember exactly how they changed it. A second is based on how long it takes light to travel in a particular wave of a particular atom. And a meter, again, there used to be a stick that was a meter long. And they'd say, this was a meter. If you want to make a meter stick, compare it to this. And then somebody would make that and take it back to Kentucky. And then everybody in Kentucky would come and measure their meter against that. And they've changed it now into terms of how far light travels. Calories is also a metric unit, but it's not the SI unit. This one is based on what happens to water. We'll get into more details on that. So those are the 2 that we'll use in this chapter. Sometimes you'll see BTU, that stands for British Thermal Units. That would be used for things like a furnace or an engine. They might talk about how many BTUs does this put out. So we're thinking about, okay, well, if I'm wanting to heat my home, how much heat can this furnace produce? We won't really use it, but you might hear it from time to time. And then if we're dealing with something really small like electrons, the energies are really small. And so these units are just too big to measure them. The joules would be like 10 to the minus 19. So you'd have like 0.0000000 18 times, and then you would have 1.5 or something. That's just too small to deal with. So instead they use EV. So in our next chapter, when we talk about electrons, you'll see EV from time to time. All right, so those are our units. You probably remember from a middle school class somewhere that we have energy divided into potential energy and kinetic energy. So we can take most things and divide them up. Potential energy is stored energy. So you can think of this as stuff that isn't necessarily moving right now, but it has the potential to move if I stop resisting that. So if you've never had physics, gravitational potential energy is the idea that if something is up, it has the potential to fall. So you have the energy, potential energy, by virtue of the fact that you're not on the ground floor of this building. If the floor disappeared, you would start moving down. Okay, so we have gravitational potential energy just by where we are. Sometimes it's called positional energy. Elastic potential energy is like the idea if you stretch a rubber band or if you compress a spring while you're holding it, it's not moving. But if you let go, your rubber band goes flying across the room, your spring goes flying across the room, as many a child has discovered in the presence of a sibling. Chemical potential energy is based on the idea that some molecules are more stable than others. So if I break bonds and form a more stable molecule, I can release energy, usually in the form of heat, and have other molecules be moving faster. So we talk about chemical energy. Sometimes you'll see potential energy written on the graph for the chemicals. And then electrostatic is the idea that if I have two charged particles, say a positive and a negative, and I put them close together, once I let go of them, they're going to come towards each other, right? So this is very relevant to chemistry. If I have a nucleus, which is positive, and an electron, which is negative, they want to get close together. And so a lot of what we'll talk about in the next chapter is going to be that potential energy between the electrons that are outside the nucleus and the nucleus that's on the inside. Kinetic energy is things in motion. So we already know that gases, when they move, have temperature associated with them. So we call that the thermal energy. That's true of everything. We just happen to talk about it with gases, but it doesn't have to be a gas. Sound is the energy of the vibration. So it could be your voice, or it could be a musical instrument, or just knocking on something. Those vibrations move through the air, hit somebody's eardrum. The eardrum starts to move, and therefore you end up having the perception of sound. The movie Alien has the tagline, "In space, no one can hear you scream," because if there's no air there, there's nothing to move. And if there's nothing to move, that sound doesn't exist. Okay, so if you're in space and there's a vacuum, people can't hear you scream unless you're on the same spaceship. But like in a different spaceship, they can't hear you scream because we can't have the motion of the air that sends that sound along. And then electricity is the kinetic energy of electrons. Now, radiation kind of fits into sort of an awkward position, because some people will put it in with kinetic energy because you have light waves that are moving, so that's motion. But remember, our formula for kinetic energy is 1/2 mv squared, so it has mass in it. But light doesn't actually have mass. And so some people will put it into a potential energy because it has the ability to cause other things to move. It has the ability to cause other things to warm up. So we think about the radiation that warms food or warms us if we're out in the sun. So I just don't put it into a category. I just kind of leave it out. But radiation is also a form of energy. Okay, so we can move between these different kinds of energy. Any process that we do typically is changing from one of these forms to another, or maybe it's moving from one object to another with the same form. So, I might have the sound from my vocal cords, it being sound in the air, being sound on your eardrums. But we change where the energy is or the type of energy, but it doesn't disappear. So we'll get back to that idea later. Now we're going to focus mostly on thermal energy. So we have to measure that with thermometers. I understand that in lab, you guys at the beginning of the semester used the thermometers that had the red liquid in it, so you could measure things. Those are alcohol thermometers. Anymore, it's pretty common for people to use the digital thermometer. So I don't know how much longer we're going to have students that really know what those alcohol thermometers are. But the idea of both alcohol and mercury thermometers is that you have the liquid in the bulb at the bottom, and that as it warms up, it expands. And with mercury, it expands in a very precise, predictable way. So this is long the standard. And you could get very, very precise measurements with the mercury. Unfortunately, mercury is toxic. So that's one bad side effect. And also, if you break a mercury thermometer, you get little tiny balls of mercury that go rolling around the bathroom floor. And they kind of look like they're fun to play with for toddlers and little kids. And so there may or may not have been many mercury thermometers in the 70s and 80s that got broken intentionally by kids who just wanted to play with the mercury, which is not a great thing. So we don't use those anymore. Now, we also have bimetallic thermometers. These are typically used for like thermostats. And so you have two metals, brass and steel. So these are alloys. I don't have steel on the periodic table. It's not an element. Brass is not an element. They are mixtures, solutions of metals. So steel is almost all iron. Brass is a mixture of zinc and copper. So they're all in that first row of transition elements there. And it turns out that while they both expand or get bigger when they warm up, one of them expands faster than the other. The steel expands faster than the other. So instead of the whole coil just getting bigger at once, the inside gets bigger faster. And so it starts to uncoil, right? And so where this thing is moves relative to where it was before. So this isn't actually showing a great picture of it. Oh, they're showing it on the top part. So where this thing is moves relative to this. It starts to uncoil. And so you can have like a little marker there showing you what the temperature is, and it just adjusts based on the temperature around it. So we got a little image here that kind of shows you this with fire. Now, obviously, we don't do this with fire in our homes. The temperature change is much smaller. But you can see it uncoiling, and then when he takes the flame away, it starts to coil up again. So in that case, the end here is fixed and the middle moves, whereas on our picture, the oops, wrong one. The other one was fixed. This picture here, let's see if I can get it bigger. This is kind of showing what's going on. So here are two layers, right? And showing the different expansion. Okay, anyway, back to our slideshow. Okay, so some symbols. Heat is represented by Q. Sorry, I did not make that letter of the choice, but that is what we use. We will use H for something else later in the chapter. And heat is when thermal energy is transferred. So a lot of times people will think of it as like a liquid or something. It's not an actual physical thing. It's not a fluid of any kind. It is just a measurement of how much energy went from one object to another or one location to another. So if I think about a hot pan that's come out of my oven, I have the iron that's on the pan. They're pretty heavy compared to the carbon and oxygen in my finger, and they're moving really fast. They have a lot of thermal energy. And if I were to touch that pan, nothing that's part of the pan becomes part of my finger, right? There's nothing that has left the pan. The only thing that happens is my finger cools down the pan in that spot, and that pan makes my finger molecules start moving a lot faster. Okay, so we didn't transfer any matter. We just had the energy of motion. What things were moving faster or slower was changed. So heat is about changing where the thermal energy is. Work is measured as force times a distance. So force is made up of both the mass that is moving and the acceleration. So we have the acceleration due to gravity, and then we have the mass. And so there's less force involved in lifting up a ping pong ball, which has a small mass, compared to a book. And that's less than picking up a big old dog that shouldn't be on the couch, right? So the more massive something is, the more force that is required, and the more force, the more work that was done. Okay. Now, we don't do a lot of work with chemistry. We normally think of things as they're just in the beaker, but we do have gases. And so any work that we have with chemistry is typically gases expanding. And so you might think, well, how does that work? So if you have pistons in an engine, that expanding gas causes the pistons to rise. And if you have a turbine at an electrical power plant where you have basically a big fan that's moving, well, we have in steam turbines, we have the expanding steam pushing the wind turbine. Okay, so the work that is coming from that expanding gas is causing that to move. Now, if instead of steam, we're burning something like we're burning coal, the expanding gases of the carbon dioxide that are produced from that burning reaction, that also is causing that to turn. Okay, so those expanding gases are the work that's involved. So together, those two things make up what we call the internal energy change. Okay, so a couple of things. The triangle is a delta. We've seen delta in the past, and we use that to mean heat. Here, we just mean change. So this is a change in the heat. Or I'm sorry, change in the energy, not just heat. And that total change in heat is made up of the work that was done and the heat that was transferred. So those two things together make that change in heat. Whenever we have a delta, that means we're looking at the final situation minus the initial situation. In this area of chemistry, it's really important to pay attention to capital letters and lowercase letters because we mean different things by them. So a capital letter means that the really important things that I'm looking at are the beginning and the end. And what happens in between, how I got there, doesn't matter. So if I started this morning in my office and I'm now here, the distance between those places hasn't changed. So that's a capital letter state function. That is the distance from where I was. But in between, I've gone back and forth from the classroom to my office, and I also went over to the Jones Hall Nelson Suite for the high school students visiting, and then I came back over here. So I traveled a big distance. That's a lot more than what happened in between. So how tired I am is more related to all that distance. That's a non-state function. But if I'm just trying to figure out how far I went or how far I'm displaced from where I was, all I care about is where I started and where I finished. Okay? That's a lot simpler to calculate in chemistry. We don't have to monitor every step of the way. We can just say, what's the temperature at the beginning? What's the temperature at the end? So we like state functions. The W and the Q are not state functions. Those are things that it kind of matters how we did it. Okay. But it turns out that because most of the chemistry we do doesn't involve gases, we can ignore W. And if we're ignoring W, then Q is equal to a state function. And so we can kind of treat Q as if it were something that we just care about at the beginning and the end. So in lab next week, you're going to be dealing with Q a lot. And even though it's a lowercase letter, because there's no work involved, we're just going to look at the beginning and the end. All right, the other thing we're going to look at is the heat capacity. So the heat capacity is how much heat energy or thermal energy change is required to get the temperature to change by 1 degree. So we can talk about the heat capacity of an object. And that would be how much heat was transferred and what was the temperature change. So we just divide those two things. That gives us the heat capacity. Now, if I just say heat capacity, I'm generally talking about an object. So that could be my mouse here. That could be this calculator. but I can't really divide that up because inside I've got metal bits that are the electronics, and those are going to have different heat capacities than the plastic that's on the outside. So if I want to be able to scale this up or down and talk about more or less of them, what I need is called specific heat capacity. So it's very similar to heat capacity, but now it depends on the amount. And remember, our amount can be a mass, it can be moles. Technically, it could be volume. We're not going to use volume in this case. So it's going to be either mass or moles. Now, if you have Dr. Hughes for lab, she will often use a lowercase s for this to mean specific heat capacity. Not everyone does that. So if you have Dr. Fraley or I can't say her name, Dr. Banjampur. Barzanganpour. Thank you. I always call her by her first name, and so I don't get correct. Barzanganpour. I have to say that. Okay. They may not put that S there. Okay. So just kind of be aware of that. In this case, we're saying how much does each gram have? And if we're doing that, it needs to be a pure substance. So I can say for water, it has a specific heat capacity depending on how much water is there. So every gram of water has the same heat capacity, and therefore I just need to know how many grams of water I have. We will primarily use the lowercase c. Later in the chapter and perhaps next semester, we may end up using the capital C, which is in moles. So instead of saying how many grams of water do I have, I might say how many moles of water. And since there's a molar mass of 18, that's going to be the difference in there. But for right now, you can kind of ignore the capital one. Okay. So section 2, we're getting into a little bit more math. We're talking about calorimetry. And so you're going to start seeing the stuff that was on that little handout extra credit thing on here. Say again. Chlorine.
You look like cool. Hey, now this word cool.
Yeah, so related to like food calories, is that what you're thinking of? Yeah, we'll see that connection in just a second. Okay, so on this whole big thing, the main thing that you want to pay attention to is this line right underneath here. Because like I said, we're mostly not going to be looking at the work, but we need to know that when Q is positive, that means energy is going into whatever we're looking at, what we call the system. And when Q is negative, energy is leaving that material or object. So that's the big idea there. Now, of course, our total energy is going to depend on the sign of Q and W. So if they're both positive, it'll be positive. If they're both negative, it'll be negative. And if they're not the same, it'll kind of depend on which way they're going. But what is always true is that if Q is going to be positive, that means heat, thermal energy is going into the system. If it is negative, it means thermal energy is leaving that system. All right, calorimetry. So we talked about specific heat capacity. This is the heat needed to change the temperature of a material per gram. Okay. And so this is where the word calorie actually comes from, is that is specifically the heat required to raise the temperature of 1 gram of water, 1 degree Celsius. Now, if you are looking on a food package, it's going to list the calories, but it turns out that the amount of energy we need to keep our bodies warm is so great that the numbers would be too huge to put on there if we just put calories. So what they actually are on the package are kilocalories. So really 10 calories on your food package with a capital C is 10,000 calories with a lowercase c. So they're really kilocalories. So that's kind of the connection there. If you go to different countries, and it depends on the country because these are both metric units. But if you go to Canada, instead of telling you how many calories are in something, they're going to tell you how many joules are in something. On the food. If you recall, near the beginning of the semester, we talked about intensive and extensive properties. So an extensive property depends on how much stuff is there. So like the mass of something depends on how much is there. But an intensive property like temperature doesn't matter how much is there. Okay, so this is an intensive property because we've already incorporated the amount into the calculation of it. So it's per gram, and so it's an intensive property. You'll notice that this formula is very similar to the one that we looked at on the previous page, but now we've got mass on the bottom. In lab, you are going to look at the specific heat capacity of water, but you're also going to have a calorimeter that has different parts to it. So when it has different parts, you can't do it per gram because the styrofoam cup and the thermometer aren't going to behave the same. So you use the other calculation for the whole object, but that means your calorimeter behaves differently than the group next to you. And so you can't use their numbers. You have to use your numbers. All right, so this is what looks like what was on the previous page, but this is how we normally see this equation, MC delta T. So M is mass, C is the specific heat capacity, and delta T, remember that delta is change, so the change in temperature, but it is specifically final minus initial.
What was C again?
Specific heat capacity. And unfortunately, sometimes people use C for both specific and non-specific. I don't know what to tell you. You just gotta like read the context clues. That's why Dr. Hughes puts the little S there. I should probably do that on this. Okay. So let's look at some specific heat capacities. This depends on what the pure substance is. So we can look at some elements. At the top, we've got mostly metals. So we have aluminum, iron, copper, and gold, but we've got some graphite in there. That's a non-metal. And we can see that all of those are less than 1, but we don't have a huge range because we don't have anything that's like 100 times less than the other. It basically goes from like 0.1 to 0.9. Okay, so I'm going to scale 1 to 10. Metals tend to be lower than other things. So most of the metals are less than 0.5. Aluminum is kind of unusually high for a metal, so it's a little bit higher. And so, we have those that we can compare to. But if we look at compounds and water in particular, water is more than 4 times that of the aluminum. So the aluminum is almost 1. Water is about 4 times what the aluminum is. And in fact, of all of the compounds that we know, water is one of the highest. It's not the absolute highest, but it's definitely way up there as far as heat capacity is concerned. And it has a lot of really useful properties because of that. So if you get burned, what are you supposed to do? Run it under cold water. So that water can absorb heat from your hand, or if you put the hot pan in the sink and run water over it, it can absorb that heat without itself becoming hot. Okay. Also, when we're trying to cook food, if we can put in enough energy by putting on the stove for a while or in the oven for a while, we can get food to a pretty high temperature. That water can conduct that heat energy into the pasta or into the meat or the chocolate chip cookies or whatever, can conduct the heat into those materials and have those chemical reactions without changing temperature a whole lot. So it will stay hot while it's doing those things. And then when you put that food on the table, but your brother's taking forever in the bathroom, and 10 minutes later, you're finally sitting down to eat, the food's still hot because it takes a while for enough heat to leave for that temperature to change. So those are all properties of water that are pretty unusual compared to other things, but that are useful. Another consequence of this is that if we look at cities that are on the coasts, they tend to have temperatures that fall in a narrower range. So while Florida and California, they're further south, so they're going to be warmer than us. They don't have as extreme temperatures as places like Kansas or Iowa. So in the center of the country where we don't have large bodies of water, there's not even a lot of lakes nearby, the temperatures can go way above 100 in the summer and way below 0 during the winter. But if you're looking at New York City, if you're looking at Portland, if you're looking at those cities on the coast, you don't see that kind of extreme change in temperature. They do have some changes, but some people joke like in Los Angeles, it's always 70 degrees. And that's because it's sitting right on the ocean. So water having a high heat capacity can kind of keep things around it fairly stable. Now, if you look at the other compounds that are near it, ethyl alcohol, that's the kind of alcohol that would be in beer and wine and things like that. And then ethylene glycol, which also goes by the name antifreeze, they both end in OH. So that's a hydroxyl group. And compounds that have that, and then water also has OHs because it's H2O, they tend to have higher heat capacities than other things. So you can kind of see those three things are a lot higher than everything else that's on the list. Wood comes closest, but if we think about it, if it's fresh wood, it's also got water in it. So there you go. The stuff on the bottom here, these aren't pure. So it's really going to depend. Are we talking pine or maple? Are we talking dry wood or green wood? Is this cement that has calcium in it or magnesium in it? So it does depend a little bit on those materials. So those are kind of less certain than some of the other things. And that's why you only have 2 decimal places instead of 3 decimal places, because it depends on some things. Okay, so we are going to look at this question here. Okay, so if we look at this equation from the previous page, we've got mass, specific heat capacity, and delta T. And so in our question, how much heat is given off by 18.3 grams of iron? That's going to be our mass, going from 91 to 37. So it doesn't list a specific heat capacity. So we'll have to look at a table over here, and we'll see that it's 0.5. All right, if you are looking at the temperature change, remember we put the final first and then we do the initial. So which one's the final temperature, the 91 or the 37? The 37. It matters what order we put it in, okay? So we're going to put 37.0 minus 91.0. And that's going to give us a negative number. I recommend, much like with R that had a lot of units, when you have your heat capacity, put the units in there so you can keep track of what's being canceled. So in here I have grams being canceled and my degrees Celsius is going to get canceled and I'll be left with joules.
Are you gonna always give us the heat capacity?
Yeah, there would be no reason to memorize it. You will probably know what water is by the end of the unit because we'll use it all the time, but I won't make you memorize that. Okay, so if you remember PEMDAS, or please excuse my dear Aunt Sally, parentheses comes first. So we have to do this subtraction first. And when we do that, my calculator says negative 54. But we know the information for the 10th place. So I'm going to go ahead and put the 0 there. So in adding and subtracting, we're not counting the number of digits. We're seeing how far from the decimal we have information. And since I have information in the 10th place, I'm going to record the 10th place there. And that's going to be degrees Celsius. I'm going to come back to the temperature in just a minute, but let's go ahead and finish plugging these things in and see what we get. Yeah. You mean this?
Yeah.
That's a 4 or 5. That came from the table over here. So you will always have to look that up. That's not something to memorize. Now the question may say iron has a specific heat capacity of 0.450. So that would be the version of looking it up. Yeah, Mason.
Would you ever knock us off that we forgot to put like the S, like the little S?
No.
No.
Like I said, people don't always put it anyway, so I'm not used to putting it. That's why I don't usually put it there. All right, so if we plug this in, this negative here is going to give us a negative overall number. And I get negative 445 joules. So you'll notice that's a pretty big number. In the last couple of classes, people were like, I don't want to tell you what I got because it seems wrong. It seems so big. Joules is always going to be a pretty big number in this chapter. In fact, sometimes it'll be in the thousands, in which case we'll convert it to kilojoules. So you do that by dividing by 1,000. We'll get to that on Monday. Okay, this negative means that energy is leaving the iron. So let's see if that makes sense. The iron started at 91 degrees, energy left, and then it was 37. Does that make sense? Yeah, so as the thermal energy left the iron and it went somewhere else and went into the water around it or the air around it or whatever, as it left, the temperature dropped. Okay, now if you're paying close attention on that table at the top, take a look at the units. It says joules per gram Kelvin, and you'll often see that. Okay, so what if we changed this to Kelvin? We can do that. So it would be 310.0 Kelvin minus, and I have to plug this one in because I don't know it. 364 Kelvin. And if I subtract those two, I'm going to have basically 64 minus 10. I'm going to end up with that same negative 54. Okay, so it's the same either way. I recommend you leave it in Celsius because a lot of times if you convert it to Kelvin, you'll convert one and not the other, and you'll suddenly think it's 364 instead of just the 54. So it's helpful to maybe just leave it in the degrees Celsius. Problem with that is I just spent an entire chapter telling you it always has to be in Kelvin, and now I'm like, use Celsius, it's the better way to go. So if you like Kelvin and just knowing that Kelvin is always going to work, just remember to change both numbers to Kelvin, not just one. Okay. Next thing. Here. The first law of thermodynamics. It's not the one I'm on, right here. So this is often called the conservation of energy. We've had conservation of mass in the past that basically said before and after our reaction, the thing happens, the mass weighs the same. Conservation of energy is very similar. Before and after some process, the energy of the universe is going to be the same. So remember we said another way to say the conservation of mass is that mass can't be created or destroyed. Same thing is true of energy. Energy can't be created or destroyed. No matter what physical process, no matter what chemical process, you're not going to change the energy in the universe. So sometimes people who want to have energy to say, run a supercomputer for AI or send a rocket to the moon or just power their houses, you might say, oh, I want a process that's going to create more energy so I can do these things. This says you can't win. You can't get more energy than there was before. All right, the universe is kind of hard to measure. It's a big place. So we're going to break down the universe into two things, the system and the surroundings. The system is the thing you're studying. So for chemists, it's going to be what's inside that beaker. The surroundings is everything else in the universe. So it's going to be the beaker itself, the thermometer, the stirring rod that's in the beaker. It's going to be if you have water that's in there with whatever your chemical reaction is, that's part of the surroundings. The air, you as the scientist are part of the surroundings. The doorknob, the chapel, Lexington, the moon, distant galaxies, all of those are part of the surroundings. But we know that my chemical reaction happening on the desk in front of me probably isn't making big changes to the chapel or the moon. So when we say the surroundings, we're usually limiting that to the things that are right in front of us. So whatever the container is, the instruments we're using to measure it with, and you, the scientist. So if I'm holding a piece of iron that is at 37 degrees Celsius and it is cooling down, it is going to feel warm to me because the heat that is leaving it is going into me. It is doing the opposite for the surroundings, and I'm part of the surroundings. If I am holding something, a piece of metal that is cold, and it warms up, that energy is coming from me. It's leaving me and going into the system. Okay, so the change in energy of the universe is the change in energy of both things, but that's equal to zero. So if that's equal to zero, we can say whatever happens to the system is the opposite of what's happening to the surroundings. So we can't stick a thermometer inside a piece of iron, but we can measure the water that the iron is in. And so we can make measurements about the surroundings and then say, whatever's happening to the surroundings, that's the opposite of what's happening to the iron. And that's what you're going to be doing in lab next week. Right? And we'll see a little better example of how that's going to work on Monday.